Okay, now let's start talking about how to calculate some of these quantities. So we've seen magnetic flux before. It's just like electric flux, except using B instead of E. So I'm going to write that down as a reminder that it's the integral of B dot n hat dA. And this is over some surface, and the n hat is the normal to that surface. Okay, so the rate of change of this quantity, that's what we have on the right-hand side here. The rate of change is going to be the rate of change of what's going on in this integral. Okay, and here we can see a couple of things I pointed out before. First of all, this gives me the component. I can call this, if I like, I can call this B perpendicular, right? It gives me the component of B that's perpendicular to the area that I'm integrating over. And so if the angle between B and the normal of the area change, then that's going to be a changing flux, and the time derivative will be non-zero. Also, if the magnetic field magnitude changes, that's going to be a changing flux, and that's going to change that's going to be a non-zero time derivative. And lastly, the area is involved in this equation. So if the area is changing, then again, non-zero time derivative. Okay, so these were the things that I pointed out qualitatively a second ago. All of them appear here in this equation. Now I need to put a negative on this so that I now have the right-hand side of Faraday's law, and I'm going to come back to this negative sign in just a minute. And now let's talk about the EMF. So we can find the EMF from the electric field that is induced by this change in the magnetic flux. And your book calls this a non-Coulomb electric field. And the EMF is going to be the integral around our loop. So this is a path integral, a line integral, around our loop of E dot dl. And this makes sense if you think about, remember that electric field is measured in volts per meter. dl is a length, so that's in meters. So volts per meter times meters should give us volts, which is what we would expect for an EMF. And so now putting all of these equations together, here's my left-hand side of Faraday's law, here's my right-hand side. So I'm going to write the final result. Okay, here we go. Here's Faraday's law in full generality here. Now, it looks a little complex, and that's because this is the most general form, and there's a lot of simplifications that can happen depending on the situation. So let me give you an example of something that is simple. One thing that could be simple is, what if B and n hat are always parallel? Then B dot n hat just becomes the magnitude of B. And let's say that the magnitude of B is changing, but the area is not. Actually, let me back up a step and recall that this is an integral over a surface area, whereas this one's a path integral around the loop. Okay, so first let's say that B is not changing on the surface, it's only changing with respect to time. So that means I can pull it out. And then I'm left with negative d dt of B magnitude integral dA. All right. And this integral dA over the surface just ends up being the surface area of A. And I mentioned that A is not changing with respect to time, but B is. And so our final result would look something like this. Negative the area of the coil times the rate of change of the magnetic field strength. On the left-hand side, if we assume that the electric field, the non-Coulomb electric field, is constant everywhere around the loop, which is a reasonable assumption if the loop is a circle, because every point on the loop is the same distance from the magnetic flux. So I can pull this out and I get N or E and C dot dl. And again, let's say that those are parallel always. So this just ends up being the magnitude times the integral of dl over the loop. And so the path integral around a loop of the length is just going to give me the circumference of the loop. So I said this was a circle, so let's put the circumference there. And this then simplifies to e times 2 pi r on the left-hand side. Okay, so this is a simplified version of this law where things are nice and symmetric and makes the math easier. But this is the fully general case. Down here, though, we can see clearly that if the magnetic field changes with respect to time, it's going to give me, if this is non-zero, it's going to give me a non-zero electric field. We could also simplify this area over 2 pi r, since this area is pi r squared, since I was talking about a circle. And I can divide the 2 pi r over. Okay, so this should be enough information to get you through checkpoint 4 in chapter 22. There's one more remark I'm going to make. Okay, so you see for this situation, I was talking about a single loop. Okay, and we were looking at the circumference of that loop. Up here, what do I do if I have more than one loop? Well, there's a couple of ways of thinking about this. One is that, well, I think both of them come down to thinking of this as a stack of loops. Even though it's all one wire, we can think of it as a stack of loops. And if we have n loops, then what's the total area that the magnetic field lines are penetrating? Well, it's this area that I already called A, but you can think of there's an area A for each one of these loops, and the magnetic field lines are penetrating all of those areas. So you could say that the area, the effective area for a solenoid is N times A. So let's see what that does in Faraday's law. So what that's going to do is it's going to multiply the area by a factor of N, the number of coils. And that's a constant because we're assuming we're not changing the number of coils in the solenoid, although I guess that is a possibility. But for our cases, it's not going to happen. And so having N coils effectively increases the area by a factor of N, which effectively increases the flux by a factor of N. So Faraday's law then becomes this. Okay, where I multiplied the flux by a factor of N and I pulled the N out because it's not changing with respect to time. Otherwise, it's the same equation as before, but we see the important reason why we would want to use a solenoid for something like this if we're trying to create electricity. If I have one coil, then I get a certain EMF, but if I double the number of coils, I get twice as much EMF. If I have 1,000 coils, I get 1,000 times the EMF. Okay, so this is a very important reason why solenoids are used in electricity generation.